On a planet far away in space, there lived an alien father who happens to be a master in calculus. He is pretty handy with technology, and he is in his home trying to finish his spaceship to go to Earth by using first and second derivative test machines and curve sketching to create the pieces. This is when his alien son, Billy, suddenly comes in to talk to his father.
Daddy! I want to help you build a spaceship and learn some more calculus too.
That's my son, always learning calculus. But are you sure you won't break anything?
I promise!
Alright, my son, but make sure you can keep up with my lesson.
Yay! Calculus time!
His father is demonstrating how he can turn a big block of titanium into a piece for the spaceship by using their first and second derivative test machines and curve sketching methods.
Now, my son, we are here at our first derivative test machine, and what has appeared on the monitor is our equation.
Where did the equation come from?
I will tell you that each block of titanium represents an equation. It's an equation that we must solve correctly by using first and second derivative tests and sketching the graph correctly. We must do all these steps before the titanium can be processed by our derivative test machine.
We also have to find the second derivative and graph?
It's actually not too difficult. Besides, we only have one more block of titanium left, and we must solve the equation of the titanium block to create the very last piece to the spaceship.
So Daddy, how do we use this first derivative test machine?
I will show you, my son, and then maybe you can try it. Now, the first step to solving our equation f of x equals x cubed minus 3x squared minus 9x plus 1. We must find the x values of our critical points by taking the first derivative.
So what are these so-called critical points?
A critical point of a function of a real variable is any value in the domain where either the function is not differentiable or its derivative is 0.
And we have to find them using the first derivative? How do we do that?
We can use Leibniz notation for derivatives. It's a shortcut. We can use the power rule theorem.
How does this equation work?
So, our equation is fx equals x cubed minus 3x squared minus 9x plus 1. And basically, what we do is take the exponents to the front and subtract 1 from the exponents. And basically, the 1 goes away in the end. And when we simplify everything, our first derivative will equal 3x squared minus 6x minus 9.
So we found our first derivative. Now how do we find the critical points you mentioned earlier?
Now, to find our critical points of our first derivative, we will first factor.
Why factor?
It will always be easier to find critical points if we factor the derivative. So we are going to pull out the common factor of 3, and that leaves us with x squared minus 2x minus 3. So this is our derivative factor. And since we are looking for critical points, do you remember what critical points are, Billy?
A critical point of a function of a real variable is any value in the domain where either the function is not differentiable or its derivative is 0.
You remember well. Since we need to find where it is 0, we need to set our first derivative to 0 and solve for x.
I can solve for x. It's really easy.
Okay, Mr. Smarty Pants. Then what does x equal?
X equals -1 and 3.
Good. So we have 2 critical points. And next, we'll look at the sign of the derivative to see where the graph is increasing and decreasing.
How can we do that, Daddy?
On the number line, we can plot all of our critical numbers and use numbers between the intervals to plug back into our derivative. You don't want to plug these numbers back in the derivative because that's what gives you 0.
So do we take numbers inside of each interval?
If we take a number smaller than -1, say -3, we go back and put it inside the derivative. If we put -3 into the derivative, what do we get, Billy?
Positive 36.
It sure is! And what positive 36 means is that the derivative is positive for any number less than -1. Now, we are going to take a number between -1 and 3. How about 0? What does that equal?
-9.
That means that the derivative is negative for any number between -1 and 3. Lastly, we are going to take a number larger than 3, say a billion, and put that in the derivative.
Then the number will become positive, Daddy.
Yep. The idea is, wherever the derivative is negative, that's where our original function is decreasing. And wherever the derivative is positive, that means our original function is increasing. Understand up to this point, son?
Most definitely.
Here is something to note for first derivative test, Billy. If f prime of x changes from positive to negative, f of x is the local maximum. If f prime of x changes from negative to positive, f of x is the local minimum. If f prime of x stays either positive or negative, f of x are neither max nor min.
Does this mean -1 is our local max and 3 is our local min?
You catch on pretty quickly. We have finished solving the first derivative, Billy,
Yay!
but we still have to find the second derivative. Now, Billy, press this button to tell our first derivative test machine that we found and solved the first derivative. It can now process the block of titanium. Billy, why don't you try solving the second derivative?
What? What if I mess up?
You won't. I showed you all the steps when we did the first derivative. The steps are exactly the same. You're just solving for the second derivative this time. Don't be nervous.
Okay. So now I'm going to find the second derivative from our first derivative by using the power rule that you mentioned earlier. And in the end, our second derivative is 6x minus 6.
Good. Now that you have found the second derivative, find our critical points.
We need to find where it is 0. So we set our second derivative to 0 and solve for x. And our critical point is x equals 1. Now do we look at the sign of the derivative?
Of course.
I will make a little number line and I'll plot our critical points. Now I will take numbers inside of each interval.
Wait, Billy. You should also plot our critical numbers in the first derivative.
Why?
You will find out when we are about to graph. It doesn't make a difference when finding the signs of the derivative.
Now I will take numbers inside of each interval. So if we take a number smaller than 1, say -2, and we go back and put it inside the derivative, we get -18. This means that the derivative is negative for any number less than 1. Now we are going to take a number larger than 1, say a billion, and put that in the derivative.
So, any number larger than 1 will be positive, right? Now, Billy, did you find any inflection points?
There's one at x equals 1. It's where a curve changes from concave up or concave down.
Yes. If we look back at our first derivative, our local max is -1, and our local min is 3, where one is the curve should look something like this, because it changes from positive to negative. And where 3 is, the curve should look something like this, because it changes from negative to positive. This is why I told you to plot all of our critical points from our first derivative.
Oh, I see. So can we sketch the graph now?
We sure can, my son. Let me bring up the graph. Okay, why don't you try the graph, Billy? And remember, -1 is our local max and 3 is our local min. Do we have any intercepts, Billy?
Oh, yes. 0, 1. I will graph it now. I did it!
Press the button to find out if you graphed it correctly.
Daddy! I did it!
Well done, my son. You now understand your derivatives and how to curve sketch.
Hey! I actually do!
Okay, son. Our suffering is finally over. We finished the spaceship together and you know how to solve first and second derivatives and curve sketch. You should be proud of yourself. Ready to go to Earth?
You